So through this exam revision that we are having, we are going to notice that is transistor amplifiers. This is from the question paper of November 2023. Given question 3.1, the following values of a common emitter amplifier. We are told that it's a common emitter amplifier, which is fine. But looking into the information that we are given, we can see this part, RB1, RB2, they can give us to calculate these ones, or they can give us like this. But being given this, it is simply telling us that we are dealing with a common emitter amplifier, yes, but that is of a voltage divider. That is of a voltage divider, a common emitter amplifier. So you must be able to tell so that the formulas that you're going to use are those ones for a voltage divider, common emitter amplifier. I talked about those formulas on an introduction, so you can go through the video, check all the formulas of everything that we are given here, how to relate these. So we are given to calculate the values of this information, VC, IC, all this. Okay, so let's take the first part, that is 3.1. Just gonna start with VE and see if it is able for us to calculate this VE. From our calculations, we do understand from our formula sheet, VE, we are given these calculations here from RE. If you are to consider from RE that RE is equal to VE over what? Over IE, which approximates to VE over IC. So we can think along the lines from that. Okay, so let's think along the line from what we are given, that RE. Okay, since we cannot have this one straightforward, we can think of RE being equal to VE over what? Over IC. The IC representing what? IE. Remember that IE is actually approximately equal to IC. So you just use IC there. So in this case, we can make VE the subject over 1 cross multiply. So you end up with our VE being equal to RE times IC, which is IC RE. So the question is, are we having these values? IC. Are we having the IC here? Okay, on this information, IC we do not have. Actually, they want you to obtain that. So this one cannot give us direct. So guys, this one was gonna limit us, as we can see. That's a limit there. That's a limit. Let's use this one, VCC over 10, because VCC is there. Okay, guys, I wonder why I couldn't take this one direct and straightforward. So this one, we're gonna use it to calculate IC, because IC is there for needed, and we do not have that. So let me just have it here. So our 3.1, our VE from VCC over 10, it can be calculated 1 over 10 of VCC, because VCC is there. Okay, VCC is 12, so that's 12 over 10, and that was going to give us the value of VE, which is 1,2 volts. All right, so let's just have it here, 1,2 volts. Then IC from this one, now we can calculate IC there. Okay, so you can just manipulate IC will be equal to what? VE over RE. So you divide there. So it'll be VE over RE. So IC can be calculated. So IC was going to be VE. We calculated this 1,2 over RE. Are we having the value of RE? That is 120 ohms. So we are given this. So that was going to give us the value of IC, which is 0,01 amperes, or we can write this as multiply by 1,000 or 10 to the exponent of 3 to convert to milliamps. That is going to give us 10 milliamps. So we have got the value of IC as 10 milliamps. So the question is, can we calculate this from any other formula? There are so many formulas that you can have, but in this case, we could have been limited to this. If we were given IB, but if you check now, they need you to calculate that IB. If you were given IB, you're going to use the beta to calculate that, your current gain. So since we now have IC and we want to calculate IB, we can use that bit again to calculate IB, because these two, they form a relationship again. I talked about that. If you've forgotten, guys, the formula sheet is always there as an assistance. The part of the beta here, which is IC over what? IC over IB. So if you were to manipulate that, you can make IB the subject. Remember, we are on IB. So if beta is IC over IB, you cross multiply, is going to be beta IB equal to IC, and we need IB. So we can divide by beta. So this was going to give us the value of our base current, which is IB, that's IC. We just calculated this, 10 milliamps. So that's 10 times 10 to the exponent of -3 over B, our beta, beta there, which is 250. So dividing this, it was going to give us the value of IB, which is 0.0004 amperes, which you can just convert to microamperes by multiplying by 10 to the exponent of 6. It gives us an answer of 40 in microamperes. So that's our IB in that case, right? So you can just use it, you can calculate from the beta there. So IB, have it. In case we'll need this current, we can simply relate to that one that we calculated. It can be used to calculate any other value in case that it is required. Then we move on to another value, which is VCE. Since we are talking of a voltage divider, definitely RE is to be considered. Where RE is considered, it means VE is considered, just like what we saw. So it means on our calculation of the VCE, VE is supposed to be involved. We are supposed to have that. So if you check on the calculations, you see that since we have RC, there's this formula for RC, that we have two formulas. There's this one, and there's also this one. So if you take, because we are considering where the VE is considered, there's a voltage divider. So the formula that you're supposed to consider where RC is this one. So let's think along this formula and see, because you can see that RC is there. VCC, we just save it. We have this one. VE, we calculated it. IC, we calculated it also. So we can calculate our VCE from there. All right, so let's try make this the subject of the formula from the formula that we just had. We saw that RC was supposed to be given as VCC minus VCE minus VE over what? Over IC. And what is it that we need? VCE, which is this one, VCE. So you're going to make this the subject of the formula. From what we are given, we can simply manipulate, make this the subject. So cross multiply, that was going to be IC times RC is equal to 1, multiplies everything that we are seeing here, which is the VCC minus the VCE. We're going to subtract everything, the VCE and the VE. What is it that we need? The VCE. So we can simply make this the subject, take it to the other side so that it becomes a positive there. So it will be VCE is equal to everything that we have on the left-hand side, the VCC. I mean, on the right-hand side, we've got the VCC. We also have the minus VE. Then we take the IC, RC this side so that it becomes a negative. It is a positive. The moment it crosses the equal sign there, it becomes a negative. Be very careful as you manipulate your formulas. So that is the formula that we are going to use to calculate VCE. So with this formula, we can simply substitute our VCC. Everything is there. We calculated, we have this VCC that is given. We have got our value for VCC here. Guys, I remember this from my presentation. I have this value as 12 minus the VE that we just calculated. Remember, we calculated this 1,2. So you're going to subtract the 1,2 minus IC. We calculated also IC. IC, we got 10 milliamps. So that is 10 times 10 to the exponent of -3 times RC, which we going to use as 480. We have got the value of RC, 480. So that is simply substituting into the formula was going to give us the value of VCE. And that was going to give us 6 volts. Okay, so we have got the value of VCE for making it the subject when we consider RC. So that's our VCE, 6 volts. In case you might need that. The last part was to calculate VB, which is our base voltage, and VB can be calculated. We can consider, because we are given RB1 and RB2, we can consider the voltage division in order for us to calculate our VB. There are 2 formulas actually that you can use. So I want you to get your formula sheet so that you understand this. So VB can be calculated from these 2 formulas. The VB here, which is VE plus VBE, it can give us the value of VB. And also there's another VB that I need us to consider of the voltage division. Okay, the VB that you can actually calculate. All right, so in this case, no problem. We can manipulate it from the Z1, Z2, this one. From any of these, is it from this here? We can make VB the subdivision. From there, the VB was going to be written as, all right, so let me just write these formulas, guys, but I think I listed these formulas on the introduction, so you can also relate from the introduction video. So the first one, it is VE plus VBE. This one is going to give us VBE. It's going to give us VB, or we can calculate from the voltage divider, those RB1 and RB2. So the formula is stated to be RB2 over the sum of RB1 plus RB2 times VCC. So this can give us the value of VB. So let's start with the easier one, guys, because we've got this VE and VBE there. Calculated your VE, this one, 1,2 plus the VBE. We are given a VBE there, 0,7. So it was just a matter of substituting. We have got the value of VB, which is 1,9 volts. With this one, you're still going to obtain the same thing using your voltage division part. RB2, 3 kilo ohm, 3 kilo, that's 3,000 over the sum of these two. RB1, if you multiply this by 1,000, the 15 comma there is going to be 15,947, okay? Plus RB2, the same 3,000 that we had before. Everything that we are having here is supposed to multiply the VCC. And our VCC is 12 volts as we are given before. So that is the condition of our question. You can have your VB from there. And that was going to give us 1,9 volts. So you must consider with the condition of the question and the formulas that can be used. Some formulas, they can work hand in hand, as we saw from this one for VB. So it's your choice. Which one are you going to use from there? So the VB, you got 1,9 volts, like I said there. The formula was in your hands. Which formula were you going to use? On 3.2, they are saying we need to calculate the input impedance, which is ZI, and the output impedance, which is Z out. Of the circuit in question 3.2, of the circuit that we had in 3.2 of the voltage divider. Remember I said it's a voltage divider. But they are saying using approximate method on a voltage divider. I explained before on our introduction. It's going to take you through. I think I still have that part of our introduction so that we can relate to what I explained before, and now using the approximation method to relate that part and see how it can be. Okay, I think it's this one here. If we can check, I explained this one. Okay, if you still remember, when we had our voltage divider, this part of our voltage divider, RB1, RB2, and I explained that we can use the precision method in our calculations. You consider all this part. So you see that the part of our precision method, or which is our precise method, actually, there we are talking about the precise, which is precision, precise method. Precise method. You are going to notice that in terms of the simplification that you have, in terms of the simplification that you are going to be having, the condition here is going to remain the same. The only part that you approximate when you are using approximation method now is this part of the gain. This part of that is where you can have those approximation, the current, the voltage, this part of the Z1, the Z2, there will be approximated values. Remember, before you were calculating Z1 properly, I want you to get, so that you understand me here. You were calculating your Z1 here. I want you to be very, very careful here on this one. This was your precise method where you are using to calculate your Z1. But this time, using approximation method, you are no longer taking Z1 like this. You are now taking this Z1 as HI. So Z1 is now approximated to this. The same with the Z2. Z2, these are approximations that we are seeing there. These are now approximations that we are making. So on the approximation method, the first thing is on the ZI, because you need to consider the input impedance there. You need to consider the input impedance. All right. So let's consider that, because an approximation is, you're no longer using the precise one, the way you're using those calculations. No. We are no longer having this part. Remember, I explained also from the first, but if here, I'm going to take you back. Explained all this, guys, if you still remember here. This was on a basic, when it is a basic without the resistor on the emitter, we had this one. And we had all the calculations that we had considering how to determine the Z1, how to determine the Z2. That's the precise method that you are dealing with. This time you're not considering that, no. So let's start with the Z1. But like I said, the condition is not going to change about the Z There you are not supposed to be confused. The Zn, which is the input, at its condition, it is not going to change how it is related. When I'm saying how it is related, I'm simply saying here, if you check your Zin, because you're dealing with a parallel combination, so your Zin is going to be a parallel combination of RB1 and RB2, which is RBT, like I explained, times Z1. The Z1 is the only part that is to be approximated. Otherwise, all those conditions, guys, that you had when you are dealing with equivalent circuits, you're going back as it is. Nothing has changed. So we saw that it will be Z1 in parallel to what? RBT, because we've got a parallel combination where by approximation now, Z1 is no longer equal to that formula that you were used to. No, it's no longer this one. It's no longer this. But Z1 is now equal to HI. That is by approximation. Z1 will be equated to the input impedance. Z1, not ZI. ZI is the input, the whole of the entire circuit. But it's Z1. So Z1 will be approximated to HI. This is where the approximation plays a role. That is what? By approximation. So if we approximate that Z1 is now equal to, we are no longer calculating it. We are now just taking it because HI is there. We are just taking it, 1,2 kilo ohms. So this is the only part that has changed. We are no longer doing all those calculations. You start to calculate Z1. But the condition there is not going to change about Zi because it is related to Z1 and RBT in parallel as we saw on our equivalent circuit diagram. So meaning say we need RBT from RB1 and RB2. That is where RBT is taken from those voltage dividers. So from the voltage dividers, I said RBT is RB1 parallel to RB2. So you can write it on the formula here, or on this RB. So it's going to be RB1 parallel, or you calculate it, then you calculate the parallel. It's up to you. So meaning to say, that's simply the product over the sum. RB1 times RB2 over the sum of these two. As we saw, our values of RB1, guys, as they are 15,947 kilo. That is kilo ohms times 10 to the exponent of 3, which is going to be 15,947 times RB2 as it was 3,000, which is 3 kilo ohms. That's 3,000. And the sum, you have to add these two. So by adding, divide everything, you're going to obtain your RB2 as 2,524,991 ohms. That's RBT that we need now to calculate the ZI here. So the ZI now, we approximated that Z1 is equal to HI. So then we need the product over sum again. Because we now have these two, guys. We have these two. Z1 and the RB. These are the ones that we need. So product over sum, Z1, RBT over what? Z1 plus RBT, like that. So that was going to give us ZI, the input impedance. What is approximated is ZI. Then we calculate it from there. So Z1, that is 1,2 now. 1,2, which is 1,200. So that's 1,200 times RBT as it is 2,524,991 over the sum 1,200 plus 2,524,991. So that is going to give us the input of 813,422 ohms. So I want you to relate with your question papers, work out as many question papers in simplification so that you can see how the questions can be given in terms of this part. You can see how questions can also be related. All right, that is an input. When I check the output, all right, so remember your values. Somehow you might need to use one or two of the values. So that is the approximation. ZI is not affected by the input condition. It is the Z1 of the transistor that you affect. The same with the output. The same on the output to calculate Z out. At the output, you are not affected to say what is the no. You're not affected. Remember what we had before on our normal configuration of this voltage divider. When you're dealing with the voltage divider, what I explained. At the output, this part is not going to affect. It's not going to change. What is it that you have there? It's the ZL and the Z2, where in this case, we just have RC. So we consider RC and what? And Z2 in what? In parallel. That part is not going to change of Z out. The Z out being the Z2 parallel to what? To ZL. But as we consider that we do not have RL, so we take ZL to be equal to what? To be equal to RC. That is the only condition that will matter to say this ZL, since we do not have RL, so our ZL will be equal to RC. So in place of this, we are just going to have our formula as Z out is equal to Z2 in parallel to what? To RC. The formula, this one is not going to change. This one, it does not change. The only part that will change is the approximation part of the Z2, the part of the transistor only. Remember, Z2 is the impedance of the transistor only. Instead of us using those calculations that we had when we were dealing with the precise method, when the Z2 is calculated like this, we are no longer doing like that. We are now approximating that Z2 is equal to what? 1 over HO. That is the only part that has changed. Z2 is now approximated to 1 over HO. So that is our approximation. So where Z2 is 1 over HO. That is by what? By approximation. This is our we have approximated there. So meaning you say we are no longer calculating the Z2 the normal way that we are used to. We are just taking our HO, 20 micro. So that is 20 times 10 to the exponent of -6. That was going to give us the value of Z2, which is 50,000 ohms. So this is 50,000 ohms, where we are simply talking of the 50 kilo ohms. With the Z2, we now consider to say, what is it about the Z out? It is a parallel combination of Z2 and RC. So therefore, we're going to consider that parallel product over sum Z2 by RC over the sum Z2 plus RC. So let's substitute. Z2, we take this from our that is where the approximation played a role. So that's Z2, 50,000, 50 kilo ohms, 50,000 times RC. Our RC, remember, it is 480 we are given. That is 480 over the sum. We add 50,000 plus what? Plus 480. This will give us the value of Z out, which is the output impedance. And that was going to give us 475,436 ohms as our output impedance. From the approximation, this is by approximation, we approximated the Z2 is the one that is being affected. So this calculation, they are going to be there. They need you to work with the precise method. They need you to work with the approximate method. So do revise your basics, as I explained, the introduction of each and every transistor amplifier that you are given in your syllabus. So you need to go through so that you understand those basics. Otherwise, we're going to have more question papers as we move on till we meet again.